Okay, so if you haven't watched it yet, make sure you watch the previous video about position, velocity, and acceleration and see how those relate to each other. And that was mostly about falling ball objects, but the general equations on those stand true, which tell us that we can relate each of these through integration. In this case, we're going to use a specific example of how to use constant acceleration, but in this case, it changes over 3 different intervals. So you might remember we did this we did this same question back on the derivatives example, but here we're going to work at the other side now that we actually understand integrals. Okay, so essentially we have 3 parts here. We have from 0 to 2, it's a constant acceleration of 2 meters per second. From 2 to 4, there's no acceleration, so we know from that the velocity is going to stay constant. And then from 4 to 6, it's got a negative acceleration of negative 2 meters per second, so it's slowing down. So let's take this piece by piece. So when we start from 0 to 2, we know acceleration is 2. We know from the equations that we derived before that for a constant acceleration, that the velocity is going to be whatever that constant acceleration is times t plus the initial velocity. It tells us from the question, which I didn't write on here, is that it starts at rest. So if it starts from rest, the things we can assume from that is that v0 is going to equal 0 at the beginning, and that the initial position is going to be 0. So let's look at those 2 things. We can use those here. So we know that if this is our velocity function, we're starting at 0, then v of t, the expression is just 2t. And I'm going to leave it at that for now, although there will be a moment at which we'll have to come back and work with that. Okay? What we also learned from our previous example is how to get y as a function of t. Again, we could do it using integration, but we also learned from the other way that if it's a constant acceleration, we have a little bit of a shortcut. We learned from the previous videos that for constant acceleration, that y of t is the acceleration divided by 2 times t squared plus the initial velocity times t plus our initial position. And again, for this, we have those values. So we can simplify that, because we know those values, that it actually just turns out to be t squared, no initial velocity, no initial position. Well, they exist, they're both 0. So y of t for this first part just looks like t squared. And so that gives us part A, the part that goes from 0 to 2t. Okay, so we have that expression for the first part, part A, which goes from 0 to 2 seconds. Now the part that goes from 2 to 4 seconds. That one, it says the acceleration is 0. Well, if the acceleration is 0, then the velocity, which is for a constant acceleration, that acceleration times t plus v0, then v of t just has to be velocity, and I'm going to call it velocity b for right now, because it's not really the velocity of 0, because we're not starting at 0. And so what is that v of b going to be? Well, we know whatever velocity this ended at, it has to still be going at that velocity if the acceleration didn't change. So the vb that we're looking for is what is the velocity at 2. So another way to think about that is the velocity. I should have noted these better before. I'm going to call this position YA, YA, and this is for part B. We know the acceleration is 0. The velocity is going to be a constant. But that velocity v has to be whatever it was at 2. So I can just evaluate that function at 2. So vv is 2 times 2, which is 4. So vb of t is just a constant value of 4, and we know that's going to be meters per second. Because it doesn't change as we go on through time. It stays constant at that value of 4 because the acceleration doesn't change. Remember, acceleration is the derivative of velocity, so the slope is 0, it must be a flat line, which is how we figured it out before. And again, the smart thing would, and then again, I could integrate it. And so I'm actually going to do that with this next step. So let's see what that really looks like if I just really do the integration with position. So if I think back to the way I had to integrate things, I was saying that it was the integral from 0 to t of u du plus y0. Now the key on that was that every time I was talking about the function starting at 0. Here we're not really starting at 0. Instead, we're starting at some sort of time. And in this case, that time is 2. But generically, y of v of t is going to be the integral from t1 to t instead of saying it's y of 0, that y is not that I'm adding on, that y is going to actually be what's happening at t1. So there's our more generic equation. Similarly, if I had done that for VB, I would have gotten that V of t is the integral from t1 to t of v of u, I'm sorry, of a of u du plus v of t1. So those would have been the useful equations to have before. Again, it worked out easily because my acceleration was 0. It was easy to see that I just ended up with vt. But we could use that. We use this more precise term instead of the generic with zeros in it. So then y of t, what y actually ends up being, if this is 4, so what we're really doing is integrating from 2 to t. VB is 4 du plus y of 4. So I'll do that integration, and I get that then it's going to be 4 times u from 2 to t. That y of 4, I actually need to go over here and figure out what that is real quick. So let me keep this separated, but use it to go get the information that I need. So When I evaluate this at 2, I run over here and get that value. 2 squared is 4. So y of b is actually equal to 4t minus 4 times 2, that's the part inside here, plus y at 2, which is 4. And so I actually get that yb is 4t minus 8 plus 4, or that yb is 4t minus 4. So for the second part, the part where it's flat, I get a linear function for my position, and it looks like that equation. Okay, one more round. The third part, acceleration is negative 2 meters per second between 4 and 6. So let's kind of spell out the velocity part again. I can use this equation, which tells me that Vc of t is going to be the integral t1, which is 4, to t of a, we're talking about part c here, u, du plus v of 4. Again, because we're working at, this is where it connects at 4. Again, when I'm at 4, I can't just suddenly shift velocities automatically. An acceleration has to happen. So it has to line up there. So I'm going to have to figure out what that is. But as we go through, what that tells me is I have the integration from 4 to t. My acceleration is 2. Maybe I can go ahead and find that real quick. V of 4. Well, if I plug 4 into there, I just get 4. And so that's what I'm going to use back over here. So this value turns out to be 4 because the velocity across b that entire time is 4. So it must be, when it gets over at the end of it, it's still 4. So my velocity for part C is the function negative 2u evaluated from 4 to t plus 4 for that value there. Trying to keep spacing so it's still legible. So it's negative 2 times t minus negative 2 times 4 plus 4. So I get negative 2t, that's going to be plus 8 plus 4. So I get, for the velocity, I get negative 2t plus 12 is the line that represents the velocity for that third part. Once I've got the velocity, again, I can use this equation, adapt it for Vc, and the correct parameters over here. So I'm going to integrate from 4 to t, Vc, sorry, negative 2t plus 12, or negative, sorry, I got to do it with respect to u, du plus y of 4. So again, do the integration, negative 2 u squared, divide that by 2, plus 12u gets evaluated from 4 to t, plus I need that value of y of 4, so I'm going to go over here to get what that value is. That value turns out to be 12. All right. Keep evaluating plug in the numbers to evaluate my interval. I end up with negative t squared plus 12t minus negative 4 squared plus 4 times 12. That whole thing plus 12. That's negative t squared plus 12t minus negative 16 plus 48 is 32, so minus 32 inside here, plus 12 on the outside. I get that y of c is negative t squared plus 12t minus 20. And just because I've needed it every other time, and I'm probably going to need it for my graph, let's go ahead and get what yc of, let's get what the endpoint is. It's negative 6 squared plus 12 times 6 minus 20. So that's negative 36 plus 72 minus 20. It's 16 meters. So this is my expression. So I've got my expressions for everything. So acceleration was given to me. Velocity I had to do some work to get. 2t for that part, 4 for that part, and negative 2t plus 12 for that part. Position I had to do a little bit more work to get. T squared for that part, 4t minus 4 for that part, and negative t squared plus 12t minus 20 for that part. And now it wants me to actually graph those. Make a sketch of that. Okay, so we're wanting to graph that function that we just solved. The acceleration is the easy part. The acceleration is what was given to us. It starts at 2. From 0 to 2, it's at 2. From 2 to 4, not including 2, it's at 0. And then from 4 to 6, not including 4, it's at negative 2. All right. Then we wanted to graph the velocity, which is one of the things that we had to actually solve. All right, so we'll set up our axes for velocity, and we also corrected some things with acceleration, which was make sure we label our x-axis as time. And we said this was acceleration, but make sure we give it units of meters per second. Okay, so what were our functions for velocity? Well, for the first part, from 0 to 2, it just looks like 2t. So, and we know it ends at a value of 4, because we use that over here. So we know here it goes up to 1, 2, 3, 4 at time 2. And that may look like a slope of 1 just because I used 2 squares here and 1 square there. Sorry that the slope may be stretched or skewed a little bit. But yeah, it goes from 0 to 4. From 2 to 4, we know that because acceleration was 0, and because we did that and integrated, that the velocity stayed flat at 4 meters per second. From 4 to 6, we found that the velocity was negative 2 plus 12. And the key point on that is we know that it had to match up at that point of 4. Is where that came from. So we know it still goes to the point that's on there at the end, and that it has a slope of negative 2. So we know that it should look like this. We know it'll be a straight line, and that if we plug in that function at 0, it's going to go down to 6. So just reminders, this is v of t equals 2t. This is v of t equals 4. And this is v of t equals negative 2t plus 12. So the other thing we would see is if we extended this all the way out and we drew a great big graph, that line would theoretically cross 12, although we know that's not what's happening at these lower values of time. It's just what the full graph would look like for that part of the function. All right, that gives us a position graph. Okay, so for the this would be our position function. And remember, we know our position function starts at 0. And for this first part, it looks like t squared. And that at 2, it ends at a value of 4. So it looks like this. So it looks like parabola of t squared for the first 2 seconds, stopping at 4. Between 2 and 4, it looks like a linear function that goes up to 12. It looks like 4t minus 4, and it makes it all the way up to 12. So at that point, again, we have a straight line. And during this period, y of t is 4t minus 4. So again, and we know if we extended this on down, where it would cross the axis would be here at negative 4. But we don't extend that line to the axis because it just runs between 2 and 4. Then we have the last part from 4 to 6. From 4 to 6, it looks like negative t squared plus 12t minus 20. One of the key things we know on that is that it ends at 16. So it turns out that looks like a parabola that crosses here at 16, and has that shape to it. It looks like y of t is negative t squared plus 12t minus 20. What does that tell us about these things? Well, it's a negative, so it's sloped down, as we expect. We could also, by using the derivative, find that the peak actually of this point actually is at 6. So we know here the derivative kind of levels out. The velocity levels out to 0. We know that, so we know it's going to be flat there. And so there are our 3 values and their expressions. So key points we learned to this one on this case 3, where we had to get things, are these. So the key thing we learned on this one was that if we're not starting at an acceleration of 0, that, wow, you can't integrate something with respect to itself, is that the velocity is the interval of acceleration from t1 to t plus, instead of the initial velocity, whatever that velocity is at t1, and the position is the integration of velocity at t1 from t1 to t using that initial position, the position at t1 is the slight modifications we had to make there.